Semigroups and their representations, Lecture 9, Finite Symmetric Inverse Semigroups. So in this lecture we will take a closer and more detailed look at the finite symmetric semigroups ISN. So let n be a positive integer. We denote by n underlined the set which consists of the integers 1, 2, 3, and then all the way up to n. As a set, the semigroup ISN, so the symmetric inverse semigroup on n elements, consists of all bijections between subsets of the set n underlined. And the semigroup operation on the semigroup is composition of partial maps. Note that the semigroup ISN is in fact a monoid. The identity element of this semigroup is the identity map on the whole of n underlined. Furthermore, this semigroup has the zero element, and this zero element is a unique element of ISN whose domain is the empty set, so it's not defined on any element of n underlined. Let's start by discussing the cardinality of the symmetric inverse semigroup on n elements. So proposition: the cardinality of ISN equals the sum, where k ranges from 0 to n, and then we should take n choose k, square it, and multiply with k factorial. Proof. To start with, let us note that if we take an element alpha in ISN, then it has a rank. Rank is a number of elements in its domain. And this rank ranges between 0 and n. So this rank is a non-negative integer which is less than or equal to n. So if we want to construct an element alpha of ISN which has rank k, we should choose the domain of alpha. We can do it in n choose k different ways. Then we should choose the codomain of alpha, and this we again can do in n choose k different ways. And finally, we should fix a bijection between the domain of alpha and the codomain of alpha. Since both sets have k elements, such bijection can be chosen in k factorial different ways. So using the multiplication rule and adding up over all k, we get exactly the formula in our proposition. Next, let us talk about principal left ideals. Proposition: let alpha be an element of ISN. An element beta of ISN belongs to ISN times alpha, so belongs to the principal left ideal generated by alpha, if and only if the domain of beta is a subset of the domain of alpha. Proof. If beta belongs to the principal left ideal generated by alpha, then the fact that the domain of beta is a subset of the domain of alpha is of course obvious. Conversely, if the domain of beta is a subset of the domain of alpha, let us consider the element gamma in ISN, which is defined as follows. As the domain of gamma, we take alpha applied to the domain of beta. So we take the image of the domain of beta under alpha. Next, for an element x in the domain of beta, we define the value of gamma at the element alpha of x as beta of x. Then gamma is of course injective on its domain, and by construction beta is equal to gamma after alpha. Corollary from this proposition: for two elements alpha and beta in ISN, we have that alpha is left equivalent to beta if and only if the domain of alpha is equal to the domain of beta. Next, let us discuss the canonical involution on ISN. So for alpha in ISN, denote by alpha to the power minus 1 the element whose domain is the codomain of alpha and which is defined as the inverse of alpha on the codomain of alpha. Proposition: the assignment which sends alpha to the power minus 1 is an involutive anti-automorphism of ISN. The assignment is obviously involutive, so that's clear. And of course it follows directly from the construction that alpha after beta, all raised to the power minus 1, equals to beta to the power minus 1 after alpha to the power minus 1, because taking the inverse element on a subset reverses the order of multiplication. So this proves the proposition. Directly from the construction, it follows that alpha after alpha to the power minus 1 after alpha is equal to alpha, and also alpha to the power minus 1 after alpha to the power minus 1 is alpha to the power minus 1. In other words, alpha to the power minus 1 is an inverse element for alpha. So in particular, ISN is a regular semigroup. Each element has at least one inverse. We have explicitly constructed it. Let us note that this inverse is in the semigroup sense, not in the group sense. Alpha after alpha to the power minus 1 is not equal to the identity element of ESN unless alpha has rank n, unless alpha is invertible. Now we can discuss principal right ideals. Proposition: let alpha be an element of ISN. An element beta of ISN belongs to alpha after ISN, so the principal right ideal generated by alpha, if and only if the codomain of beta is a subset of the codomain of alpha. Proof: we can apply our involution, which sends alpha to alpha inverse, to the proposition on the principal left ideal, and note that this involution swaps domains and codomains, and so for principal right ideals we get exactly the same thing, with domain changed to the codomain. Corollary: for alpha and beta in the symmetric inverse semigroup, we have that alpha is right equivalent to beta if and only if alpha and beta have the same codomain. Corollary: for alpha and beta in the symmetric inverse semigroup, we have that alpha is H equivalent to beta if and only if alpha and beta have both the same domain and the same codomain. Remark: since ISN is a finite semigroup, we automatically have that the Green's relations J and D for ISN coincide, and we will shortly describe the relation J. So let's now talk about principal two-sided ideals. Proposition: let alpha be an element in our symmetric inverse semigroup. An element beta in the symmetric inverse semigroup belongs to the principal two-sided ideal generated by alpha if and only if rank of beta is less than or equal to the rank of alpha. Proof: if beta belongs to the principal two-sided ideal generated by alpha, then the fact that the rank of beta is less than or equal to the rank of alpha is obvious, because we cannot increase the rank by multiplying. Conversely, if rank of beta is less than or equal to the rank of alpha, let us fix some x, a subset of the domain of alpha, such that the cardinality of x equals the rank of beta. And now consider the elements gamma and nu in the symmetric inverse semigroup, which are defined as follows. The domain of gamma is the domain of beta, and gamma sends this domain of beta bijectively to x. So this is possible due to our choice of x. Next, the domain of nu is alpha of x, so the image of x under alpha, and for x in the domain of beta, nu applied to alpha of gamma of x is defined as beta of x. Then, of course, by construction, both gamma and nu are injective, and beta is equal to nu after alpha after gamma. And this completes the proposition. The corollary is that if you have two elements in the symmetric inverse semigroup ISN, then they are J equivalent if and only if they have the same rank. So now let's summarize Green's relations on ISN. Let alpha and beta be two elements in the symmetric inverse semigroup ISN. Then we have that alpha and beta are left equivalent if and only if they have the same domain. They are right equivalent if and only if they have the same codomain. They are H equivalent if and only if they have the same domain and the same codomain. They are D equivalent if and only if they have the same rank. And they are J equivalent if and only if they have the same rank. Here is an example. Let's describe the egg box diagram of IS2. So the semigroup IS2 has three J classes. The class which has the two elements of rank 2. So for IS2, possible ranks are 0, 1, and 2. So these describes the J classes. So the elements of rank 2, these are exactly the elements which are invertible, so they constitute the symmetric group S2. There are two such elements on a two-element set, the identity E and the transposition 1, 2. So they form a J class, which is at the same time an L class, an R class, and an H class. Then we have a non-trivial J class, the four elements of rank 1. So the element which is defined on 1 and sends it to 1, the element which is defined on 1 and sends it to 2, the element which is defined on 2 and sends it to 1, and the element which is defined on 2 and sends it to 2. So that's the J class, which consists of four elements of rank 1. It has two L classes and two R classes. The L classes correspond to the domain, so the first column is the L class, which corresponds to all elements which are defined on 1. The second column, the two elements which are defined on 2. The first row, that's an R class. This is the set of all elements whose codomain is 1. And the second row is the set of the two elements whose codomain is 2. And then we have the class which has a unique element of rank 0, and that's the 0 element of our semigroup, and that's the element with the empty domain. Now we can describe idempotents and maximal subgroups. An element alpha in ISN is an idempotent if and only if it is the identity on its domain. So for x in an underlined, we can denote by epsilon x the idempotent in ISN with domain x. Then the set of idempotents of ISN is exactly the set of all these epsilon x's, where x is a subset of n underlined. In particular, ISN has exactly 2 to the power n idempotents, and the multiplication of idempotents is as follows. If we multiply the identity on x after the identity on y, we will get the identity on x intersection with y. So in particular, this is of course commutative operation, so the set of all idempotents of ISN is a commutative subsemigroup of ISN, and since all idempotents commute, and we have already established that the semigroup is regular, it follows that ISN is an inverse semigroup. And the maximal subgroups of ISN, these are the H classes which contain the idempotent. So if we take the idempotent epsilon x, the identity on x, its H class consists of all elements with domain x and codomain x, and these are partial bijections, so these are bijections from x to x. So this means that this maximal subgroup is exactly the symmetric group on x. Next, let us describe generators. For I between 1 and n-1, let us denote by Si the elementary transposition which swaps I and I plus 1. That's an element of the symmetric group Sn, and Sn is a subset of ISN. For I in n underlined, let us denote by epsilon I the idempotent, which is the Carli epsilon on the set n underlined minus I. So that's the identity on all elements except I. So note the difference in notation. We use the Carli idempotents for epsilon x, and then this not fancy epsilon for epsilon sub I. Proposition. ISN is generated by the elements Si, where I is in n-1 underlined, together with epsilon j's, where j is in n underlined. Proof. We know that elementary transpositions generate the symmetric group. Also, the epsilon j's obviously generate the monoid of all idempotents in ISN. Also, any alpha in ISN can be written as a product of beta after Carli epsilon on the domain of alpha for some beta and element in Sn. So any alpha is a partial bijection from a subset to a subset. We can extend it to a bijection from the whole set to the set, and then we should multiply this extended bijection on the right with the idempotent which projects onto the domain of alpha. And of course this implies the claim. Corollary. ISN is generated by all elements Si, where I is in n-1 underlined, together with epsilon 1, non-Carli epsilon 1. So we have just established that ISN is generated by all Si's and all epsilon j's, but clearly epsilon j is equal to epsilon 1 conjugated by the transposition between 1 and j. And so the claim follows from the previous proposition. Now we can describe a presentation for the monoid ISN. Theorem: with respect to the generating set consisting of all Si's, where I is in n-1 underlined, together with all epsilon j's, where j is in n underlined, the monoid ISN is given by the following defining relations. A. All Si squares are equal to the identity, and here I is in n-1 underlined. B. Si's and Sj's commute, provided that I and j are such that the difference between I and j is greater than 1. So the absolute value of the difference between I and j is greater than 1. Now the braid relations: Si plus 1 Si is equal to Si plus 1 Si plus 1 for all I in n-2 underlined. D. Epsilon j squared is epsilon j, so epsilon j is an idempotent for any j. E. Epsilon I and epsilon j commute for all I and j. F. Si times epsilon I is equal to epsilon I plus 1 times Si for all I in n-1 underlined. G. Si epsilon j is equal to epsilon jsi for all I and j such that j is not equal to I plus 1. And H. Epsilon I Si epsilon I is equal to epsilon I plus 1 for all I. In order to prove the theorem about the presentation for ISN, we would need the following proposition, which describes a certain canonical form for an element in ISN. Proposition: every element of ISN admits a unique factorization in the form alpha after beta, where alpha is a permutation and beta is an idempotent, moreover such that for any elements I and j outside the domain of beta, if I is smaller than j, then alpha of I is smaller than alpha of j. So alpha is increasing on the complement to the domain of beta. And here it's important that such factorization is unique. Proof: given sigma in ISN, we have that sigma is equal to sigma after Carli epsilon on the domain of sigma. So let us set beta as the Carli epsilon on the domain of sigma. And let us define alpha as follows. We define alpha as sigma when restricted to the domain of sigma, and outside of the domain of sigma, we define alpha as the unique increasing map from the complement of the domain of sigma to the complement of the codomain of sigma. And then by construction, sigma is alpha after beta, and the uniqueness is obvious. Remark: we call the factorization of sigma into alpha after beta, where alpha is a permutation and beta is an idempotent, such that alpha is increasing on the complement of the domain of beta, the canonical form of sigma. Now we are ready to prove the presentation of the symmetric inverse semigroup. First of all, it is easy to check that the generators of ISN satisfy the defining relations in our theorem. And so we have a natural surjective homomorphism from the semigroup which is defined by our presentation to ISN. It remains to prove that this homomorphism is an isomorphism. And for this, let us start with that the relations A, B, and C constitute the usual presentation of the symmetric group Sn as a Coxeter group. So recall that A says that Si square is the identity, and B and C are the braid relations. So distant Si's commute, and the neighboring Si's satisfy the short braid relation. Okay, So let U be a word in our generators. So the relations F and G tell us how we can move epsilon past S. So we can commute epsilons and S, sometimes just like that, sometimes we have to change epsilon I to epsilon I plus 1. So using these relations, we can write our word U as x times y, where x is a word in SI's and y is a word in epsilon j's. Then of course x, that's a word in SI's, that's an element of the symmetric group. And using the relations D and E, we can write y as a multiplicity-free product of different epsilon j's. D and E say that epsilon j's are idempotents and they commute. So using commutativity, we can collect all epsilon j's together. And so epsilon j to any power is just epsilon j, if the power is non-trivial. And so we will have a multiplicity-free product of epsilon j's, and they all commute, it doesn't matter how we write. So let Q be the set of all j's such that epsilon j appears in Y. And now we have the relation H. And this relation tells us that if we have two epsilon j's, epsilon j and epsilon j plus 1, then their product is equal to Sj times epsilon j plus 1. So using this relation, we can rewrite Y as zy, where z is an arbitrary element of the symmetric group on Q. And this means that we can replace x by xz. So in particular, we can choose z such that x times z is increasing as a map from Q to x applied to Q. And this means that U can be reduced to a word that represents a canonical form of some element in ISN. Since the number of such canonical forms is exactly the cardinality of ISN, it follows that the cardinality of the semigroup, which is given by our presentation, is at most the cardinality of ISN. But since we know that the former surjects onto the later, it follows that this canonical surjection is indeed an isomorphism, and this completes the proof of our theorem. Next, let us discuss the notion of a nilpotent element in ISN and the notion of a defect. Definition: an element sigma in ISN is called nilpotent, provided that some power of this element is equal to 0. So here 0 is the unique element in ISN, which is nowhere defined, the 0 element of ISN. So for example, the element 0 itself is nilpotent. Example 2, the element sigma, which maps I to I plus 1 for all I smaller than n, and which is not defined at n, is nilpotent because sigma to the power n is 0. Example 3, any non-zero idempotent is not nilpotent, because any power of it is equal to it, and this is non-zero. And the definition of a defect, given sigma in ISN, the defect of sigma is defined as n minus the rank of sigma. So for example, all permutations have defect 0, and example 2, the 0 element has defect n, the maximal possible defect. We can describe the number of nilpotent elements in ISN of defect k. So proposition: for a positive integer n and a positive integer k between 1 and n, the semigroup ISN has exactly n factorial divided by k factorial and then multiplied with n minus 1 choose k minus 1 nilpotent elements of defect k. Proof: let sigma be an element in Sn, and let x be a non-empty subset of n underlined, and let us assume that x contains n. So to the pair consisting of sigma and x, we associate an element alpha, so it depends on sigma and x, and that's an element in ISN, which we construct as follows. The domain of alpha consists of all sigma of i's, where I is not in x. And if I is not in x, then the element alpha maps the element sigma of I in its domain to the element sigma of I plus 1. Then by construction, alpha is clearly a nilpotent element of ISN. Note that by our assumption, alpha is not defined at sigma of n, because n belongs to x. So alpha is a nilpotent element, And also, given a nilpotent element beta in ISN, we can write beta as alpha of sigma x, where x is the complement to the domain of beta in N underlined, and alpha is obtained by extending beta from its domain to the rest of N underlined as follows. So if we have an element alpha in the complement of the domain of beta, we let alpha of I to be equal to j, where j is equal to I if alpha doesn't belong to the codomain of beta, and otherwise j is a unique element outside codomain of beta that is mapped to I by some power of beta. So let us now determine when alpha of sigma x is equal to alpha of sigma prime x prime as elements of ISN. Clearly, we must have sigma of x is equal to sigma of x prime, as this determines the domain of our element, and if two elements are equal, they should have the same domain. In the two-line notation for sigma, in the second line we have the cardinality of x segments of the form sigma of I plus 1, sigma of I plus 2, and so on, sigma of j, where I and j are two elements in x, such that there are no elements between I and j in x. So we can freely swap any two such segments, and this will not change the corresponding element of ISN. Therefore, if we assume that the cardinality of x is k, note that x contains n, so the cardinality of x is n at least 1. So the total number of elements in ISN, which we can get using alpha of sigma x construction, is n factorial times n minus 1 choose k minus 1 divided by k factorial. So here n factorial is the number of choices for sigma. So sigma is a permutation, we can choose it in n factorial different ways. And minus 1 choose k minus 1 is a number of choices for x. So x contains n, that's a fixed element, and the remaining k minus 1 elements are free to choose out of the remaining n minus 1 elements. And finally, x has k segments described above, and we can freely swap them. So that's k factorial possible swappings of segments in sigma. And now the claim follows from the multiplication rule. Corollary: the semigroup ISN has n factorial nilpotent elements of defect 1. We see this directly from the previous formula, or actually from the proof. So nilpotent elements of defect 1 are exactly the elements alpha of sigma comma n. So the set x equals to just n is a singleton, and these are in obvious bijections with permutations in a set. Corollary 2, the semigroup ISN has the following number of nilpotent elements, so we sum over all possible defects k from 1 to n, and then what the summand is n factorial divided by k factorial times n minus 1 choose k minus 1. Let us remark that an element alpha in ISN is nilpotent if and only if alpha inverse is nilpotent. And a small warning: if n is greater than 1, then the nilpotent elements of ISN do not form a subsemigroup. Indeed, alpha after alpha inverse is a non-zero idempotent for any non-zero nilpotent element alpha. And if n is greater than 1, then ISN has non-zero nilpotent elements. We can also characterize nilpotent elements as follows. Proposition: an element alpha in ISN is nilpotent if and only if any non-empty subset in the domain of alpha is not invariant under alpha. Proof: if we have some non-empty subset of the domain of alpha which is invariant under alpha, then it's invariant under any power of alpha, but in particular it means that it belongs to the domain of any power of alpha, and so this power cannot be equal to 0. So this means that alpha is not nilpotent in this case. So the second situation, let us assume that alpha is such that any non-empty subset of the domain of alpha is not invariant under alpha. We want to show that alpha is nilpotent in this case. So in this case, in particular, the whole domain of alpha is not invariant under alpha, so there is an element I in the domain of alpha, such that alpha of I doesn't belong to the domain of alpha. But this means that alpha is not defined on alpha of I. Next, if you take the domain of alpha and throw I away, then this set is not invariant under alpha. So alpha applied to the domain of alpha minus I is not equal to the domain of alpha minus I. And so there is j in the domain of alpha minus I, such that either alpha of j is not in the domain of alpha, or alpha squared of j is not in the domain of alpha. And now we can proceed inductively, and by induction we show that alpha to the power n is 0, because if we apply alpha to the power n minus 1 to any element, we go outside of the domain of alpha. And finally, let us discuss the notion of nilpotency degree. Let alpha be a nilpotent element in ISN. Definition: the minimal positive integer k, such that alpha to the power k is equal to 0, is called the nilpotency degree of alpha. For example, the 0 element has nilpotency degree 1, and a nilpotent element of defect n-1 necessarily has nilpotency degree 2. Also, a nilpotent element of defect 1 necessarily has nilpotency degree n-1. And here is a non-trivial exercise. Show that the number of nilpotent elements in ISN of nilpotency degree k equals the following thing. So we have the sum, where the summand is n factorial divided by x1 factorial, x2 factorial, and so on, xk minus 1 factorial, times xk plus 1 factorial. And when the sum runs over all possible x1, x2, and so on xk, and these are vectors with non-negative integer coefficients, such that 1 times x1 plus 2 times x2 plus and so on plus k times xk is equal to n minus k. Some additional problems and questions at the end. Problem question 1. Prove that alpha inverse after alpha equals the identity on the domain of alpha. Problem question 2. Show that every two-sided ideal of ISN is principal, and consequently that the two-sided ideals of ISN form a chain with respect to inclusions. Problem question 3. Construct an example of a right ideal in some ISN that is not principal. Problem question 4. Check with all details that beta is equal to alpha of sigma of x in the proof about the number of nilpotent elements of fixed defect. And problem question 5. Fill in all the details in the proof of the characterization of nilpotent elements in ISN. Thank you very much, and see you next time.